Well, this module we're going into now is all about conservation laws, okay? And conservation laws differ from using Newton's laws because in Newton's laws, we're interested in kinematics and where are things, when and where, and all that sort of thing. With conservation laws, what we're interested in are the initial conditions and the final conditions. Okay, so we could think about those as boundary conditions if we use the language of differential equations. Okay, so where do we start? Where do we finish? That sort of thing. And what that brings to us is a whole new set of tools. So we can talk about energy and momentum. Okay, those are going to be our primary topics in this whole next block of material. So let's get right into it. And so we have seen this problem before, very recently actually, and we worked it from the perspective of Newton's laws. Now we're going to work it from the perspective of conservation of energy. So when it comes to the idea of energy, what you need to remember from physics is we had a change in kinetic energy is equal to minus a change in potential energy. And then we're going to say here plus whatever work exchange has happened into or out of the system. Okay, so the work is how our system connects to other things. So work could be just a random force acting. It could be friction acting, those sorts of things. We can think about work done by a spring, work done by gravity. That's fine. You can do that. I prefer to think about those in terms of potential energy changes. If we think about them from work, then we've got to integrate stuff. Okay. If we think about it as potential energy, then we've already got the solution to the integrals. We can just go with it. Okay, so let's get into it here, see what we've got. Our block's being pushed. It's pushed at an angle. Okay, we want to find the velocity at a certain point. Okay, right there. It starts at rest. That's important. And the spring is uncompressed. That's important. Also important, the surface is smooth. So we can ignore any effects from friction. Okay, now we want to continue to make a good free body diagram, and because that's going to be useful to us still. All right. So with our object here, obviously we've got the force from the spring. I'll call that Fs, a normal force, so it doesn't sink down. Got some weight there. Okay. Now our push there, I'm going to go ahead and split that into components. All right, so 3, 4, 5. All right, so we're going to have 400 here, and we're going to have 300 pushing down here, just like this. Now, let's put this onto a free body diagram. So here's our axes. We'll keep it simple. No need to tilt or anything. I'm going to have 400 over here, 300 down. The weight is down. Normal force is up, and then the spring force is, I've drawn it wrong up here. My spring force is actually pushing against us. So here's our spring force right here, just like that. Okay. Okay, now when it comes to energy, energy changes, and we're dealing with force and work, remember that work is the integral of F dot dr, okay? And so if our motion is perpendicular to a force, then that force doesn't affect our energy equation in any way. So in this case here, we've got horizontal motion, okay? And that means automatically normal force doesn't matter. The 300, that downward component doesn't matter, and the weight doesn't matter. So all that matters with my energy change is the 400 and my spring, okay? So let's put that into action. All right, so we've got our delta K there, and so delta K is going to be 1/2 m V final squared minus V initial squared. And that's going to be minus whatever potential energy I have. There's no change in height, so there's no position energy that way with regards to gravity. But there is the spring, of course. And so that becomes minus 1/2 K. And then we've got the final compression squared minus the initial compression squared. Okay. That takes care of my FS. Okay. So I'm treating it, instead of treating it as work and doing an integral, I'm just going to treat it like it is there. Okay. Now we've got to figure out our work. Okay. And so down here, what we're going to have for our work is we're going to have 100 ds, okay, from 0 to s. So that just turns out to be 100 s. Okay. Now, let's think about the directions real quick because it's a dot product. Okay. So the force is to the left, but the motion is to the right. Okay. And so that means actually when I do my dot product, it's negative. And so it's negative 100s. All right. So we've got two competing forces. The 400 Newton force there is trying to increase the kinetic energy of the system, but the spring is trying to resist that increase. Okay, so it's pulling energy out of it. Oh, I did that wrong there. Sorry. Sorry about that. I got confused with my spring again. I think my brain's not working too well today. See how this goes. We'll forge on. I apologize. I don't even know where I got a 100 at. Wow. Okay. So it should be a 400. And it's in the same direction as the motion, so it's positive. Just like this. There we go. Okay, so then we're gonna, that's trying to increase our kinetic energy. 400. And we'll put SF on there like that. Okay? Now, SF is going to be 5. Okay, so what else do we know here? We know that my initial velocity is 0. So that term is 0. And the initial stretch for the spring is also 0. Okay. There we go. Okay. So it's gotten a little sloppy. Let me rewrite that. Oops, I want to step back to the black. So we've got 1/2 m v final squared is minus 1/2 k s final squared plus 400 s final. Okay, and we're interested in that velocity. So here's how I'm going to work that out. I'm going to take my, I'm going to multiply through by 2. I'm going to divide through by m. So I'm going to end up with vf squared becomes minus k over m sf squared plus, this will be 800 sf over the mass. All right. Now let's put in our numbers. Our spring constant is 500 newtons per meter. And our mass with this thing is 10 kilograms. Okay, and our distance is 0.5 meters squared plus 800. That's newtons. And that gets multiplied by 0.5 meters. And then we're dividing by 10 kilograms. Just like so. All right. Plug all that into your calculator, and what you're going to end up with is 27.5. And that's meters squared per second squared. And so once we convert it then to take the square root of it, what you end up with is 5.24 meters per second. Okay, there we go. All right, now we didn't have to worry about finding any acceleration. We didn't have to worry about times of the motion or anything like that. So it's a pretty powerful tool. All right, and to be real honest, when we did this problem and we did it with Newton's second law, if I'd just been on my own, I wasn't using it as a teaching example, this is how I would have done it. I would have said, screw all this other stuff. Let's just go right to the meat of it. Okay. So, okay, let's take a look at another one of these.